So what they want to do here is add another value in. So say another student turned something in, or there was an additional sale, or for whatever reason, they're adding in this new value of 88. So we now have 16 data points and want to recompute what the new mean is. And we want to find it accurate to a couple of decimal places. So if we had all the original 15 data points, we could add them all together, divide by 16, and find out what our new average is, what our new mean is, but we don't have those data points. And luckily, we don't need them. So if we switch over to the board here, let me move these things around so I can still see everything. So let's look at what we know here. We know somebody found that sum of the 15 values, took that sum of the 15 values, divided by 15, and got 35. What we want to find is what happens if we take the sum of the 15 values, add the other one, which was 88. So add the 88, divide by 16, and that's what we're being asked for. We want to know what that new mean is. So to do that, we need to figure out what the sum of these 15 values are. But luckily, we have that relationship over here. The sum of the 15 values divided by 15 is 35. So a little bit of algebra, the sum of those 15 values, if we multiply both sides here by 15, should be 35 times 15. Now 35 times 15, we could do that up by hand, but I got a calculator here, so why not? 35 times 15 is 525, so is equal to 525. So we don't know what those 15 numbers were, but whatever they are, we know they must have added up to 525 because when it was divided by 15, it turned into 35. So over here, the sum of the 15 values, we now know that's 525. So 525 plus our new 88, now divided by the 16 data points, these 15 plus that one more for 16 data points. That's going to give us our new mean. So is that 613 divided by 16? 613 divided by 16 is 38.31. So 38.31, and that's our new mean. So the mean for our new data set, 38.31. So this question does need a little bit of algebra here. I've written this out, but you could easily have done, this is x over 15 equals 35, and x plus 88 over 16, and that's what we want. So we're solving for this x and then substituting it in. But I find it often surprisingly helpful to write out the meaning of the unknowns. That can sometimes help just structurally see what you're doing. Does that help with that question? Those of you who were fighting with it? Alan, good.
Mm.
Did that make sense, Olivia?
Yeah. Sorry.
It's not the most confident yeah I've ever heard.
Because like I was trying to do it, but I don't know, for some reason every single time I try to do it, it would just still get it wrong. Or do you know like what to do? Because I was using my calculator, but every
Mhm.
time I would type in that for that question with the 24 values on it, it would always say error.
I
And
got
I
that
just,
message and I was trying to figure out why. I thought we'd look through an example like that today too.
yeah, because it like, and then I just simply was trying to I just add all the values
Hmm.
instead of like using the square root. And like it still said that. So I was just like really confused. Like I don't know if it's my calculator because it worked with the other problems, but with
Well,
that didn't have as much numbers.
yeah, let's look at one of those because I did want to look at one of those too, as long as everybody's okay with that other problem. I kind of wanted to go through today and look at some of the ones that people were fighting with. Let's see, that would have been in here. Where's a nice example? We'll look at a couple of different ones of these because I know they all had some issue to them. Well, here's a nice
Yeah,
big
I
one.
think it was, yeah, I think it was that one.
Okay, so there are a lot of different ways we could go about finding really all of these. It is specifically suggesting that we use our calculator or Excel. So it is kind of saying, hey, let's not go through and um, crank all this stuff out by hand because that's a lot of work.
Hmm.
Even with
How do
26
you
data
use
points, it's a lot of work.
Excel?
Well, let's do a bit of both.
Okay.
So let's say we want to use the calculator. Now I'm going to move away from this screen and go to the calculator. So I'll still be able to see the data points. So for typing them in, but you guys won't be able to see them. But let's go over to that calculator. Okay, so if we want, we could simply, like I think part of what you're saying, we could try to add these all up on the calculator, divide by how many we have to find the mean, but we really kind of want to automate this process as much as possible, have the calculator do as much of the work for us. To do
Right.
that, we want to start using this stat application. So you should see the button on your calculator where it says stat.
Mm-hmm.
So I want to go to that stat and edit the stat lists. So if we go to edit,
Okay.
you should have these lists. If you've
Yeah.
done regression on your calculator, it's the same lists um, as regression.
Okay.
So under this list, I want to put all these values. So it's going to take a minute here. So 66 is one of them, 77, 29. Give me a minute. 80, 71, 81. It's another 71. Oops, I put 70. 88, 33, 37, 48, 37. Yeah, I'll just be a minute here. That is one of the things about putting things in the calculator. The big thing I don't like about using the calculator for these things is it is a little bit arduous to put this in. In Excel, you've got to type them in too, and it might just be that my hands are faster, and I'm a little bit more used to putting data into typing into a computer than putting it into a calculator like this.
Mm-hmm.
But it is the irritating part, to be sure. To be sure. Almost done. 94 and 10. Okay, so once all the data is in there, and one of the nice things is if we click on this last, sorry, I have to scroll up to that last data point, it tells us list 1 entry 24. So if I know the array I'm looking at here is 6 by 4, it has 24 data points. That's my 24th data point. So I know I at least have 24 numbers in here. Hopefully they're the right numbers. But at least I know I have the right amount of data in there. And it is good to kind of check through, hey, did I make sure I typed those all in right? So once we have that data in there, we can quit out of there. I'm just going to go second quit. That data is still in that list. Anytime we want it, until we clear the list, we can go back in and that data will be there.
Okay.
So to perform some of our tools on that data list, we're going to go back to that stat menu. And instead of sorting it or editing it, I want to go over to calculate. Now, this is, again, where you did quadratic regression or linear regression if you've done those before. But this top list, that one variable stats, is a very nice tool because it will find us all the basic descriptive statistics about our one variable data set. It's one variable because we have one column of numbers. In some of your advanced stats class, you'll deal with multi of variable systems, but don't worry about that now. We're not going to use that two variable at all in this course. So it'll just be that one variable statistics. So I want to do that one variable statistics. So I'm going to hit enter to bring that command up. Ask what list. So if we have multiple lists, we can tell it different lists, but list 1 is the list we want. Frequency list. If you've got a list of data and a list of that data's frequency, like in a frequency table, you'd give it your list and your frequency list, but don't worry about that for what we're doing. We're just typing in all the raw data. So then calculate. And again, depending on the addition of your calculator, it just might have brought the one variable stats to the home screen, in which case you can just hit enter. It defaults to list 1. But it gives us really all the information we'd ever want. Now, we do have to be a little careful here. The X bar, that's our mean, of course. So our mean is 55.75. The sigma, that means the sum. So that is the sum of our X values. So if we wanted to know what they were all added together, we'd have it. This sum of X squared does square all the values and add them together for whatever reason somebody might want that. It's here. We've got 2 standard deviations here. This S of X, this is our sample standard deviation. So if you're asked for standard deviation for a sample, you'd give this one, the 24.01. The sigma, that's the Greek letter sigma. We use Greek letters for populations. We'll do that more later this term. So if it's a population standard deviations are a bit lower. The formula is slightly different, ever so slightly different. So if it's a population, you'd use this standard deviation. But for right now, it's the S. The N24, because there were 24 data points. If we scroll down, it gives us a min. We'll talk about what the Q1 and Q3 stand for, either probably tomorrow, frankly. It might come up today, but probably tomorrow we'll start talking about these quartiles. But so our minimum of 10, our median is 52. Q3, again, we'll talk about that tomorrow. So our max of 49. So our range would be the difference between those. So 94, I think I said 49, sorry. 94 minus 10 is 84, so our range is 84. So it really gives us a lot of information as a payoff for all that typing in.
Yeah, I like this better.
Now, Excel has a similar tool. Excel also allows us to find our data in kind of discrete pieces. We can find each of them individually if we want to, as well as it does have a tool for finding, actually, frankly, all of that data and a lot more if you want it. So I can show you that real quick, because it is nice for us to be able to use both tools. So you guys can see that Excel document now, right?
Mm-hmm.
Okay, so I'm going to put the data in again and enjoy the fact that I can type and not be having to put it into the calculator again. So real-time display of that being nicer. I don't know how much faster it is. We could check the times, but it's certainly more comfortable for me anyway. That was faster, right?
Yes.
Yeah. Okay, so we've got our 24 data points in there. Let me make this a little bigger. And if we wanted to find any particular either mean, median, mode, whatever. So if we want to find our mean, let's say we want to find our standard deviation. We can do those with individual commands. So our mean is average. And it finds us the average. Our standard deviation, st dev, if we want population, .p, if we want sample, .s. So we have to know some of those commands or be able to look them up, but it finds us those same values. Nice to be able to have them individually.
Yeah.
Also, these are live, so if any of these numbers change, so like say this 33 becomes a 44, those change in real time.
Oh, wow.
So that's the super handy thing with Excel, is these are live calculations. We also have a tool under data. Where is it? I need to maximize this so I can see all my tools. A tool under data. Oh, where is it? Oh, where'd it go? Excuse me. Oh, I don't have right now on this. That's too bad. I'll have to show that to you some other time. There is a tool on Excel that I have to load up properly, and I'll show you guys how to do that when we do the lab on that, where you can highlight the data all at once and say, give me everything you know about it. It does have, I think it's 30 some odd different descriptive statistics values. So it is kind of an overwhelming amount of information in some ways, but has the disadvantage that it's not live. So the numbers don't continually update. But either tool will work if we wanted any of the other descriptive statistics, even things like range. Ranger, it's not what I wanted. We could either, try to use a range command, but we could also do things like the maximum value of the list and then subtract the minimum, min, for that list. I mean, that's how we're supposed to calculate range, max minus min. So max minus min's that same 84.
So you got to know a little bit about Excel and computers in order to run that code.
A little bit. It does take some practice to do that. Yep. And a lot of people like using the calculator instead, though the calculator is a little bit clunkier in some ways. The calculator is a little bit shorter of a learning curve, because ideally you guys are already fairly familiar with talking to the calculator, especially you guys coming out of 63 and 96. You guys have used like regression and lists for a lot of things. And if so, that's fine. You can do all of this stuff or most of this stuff with that calculator just fine. But it is nice to kind of start learning some of these new tools, because they will, again, have a lot of power to them. And there are some things that are just vastly easier to do on Excel once you get comfortable with it. So, but this, again, this isn't a course on Excel. So, you know, there are folks who get through pretty much all of it without getting too, you know, and using the calculator for most of their work, just because that's what they're comfortable with. And that's fine. I think you might remember last time I was saying, most of you, as you go on through whatever you're going to do with your with this material, Excel is what you're going to have available, as opposed to a graphing calculator. In your offices or at your desks, you'll often have that, you know, access to a spreadsheet as opposed to access to a graphing calculator. So it is nice to know these tools in spreadsheets. Oh, yeah, somebody asked about in the chat about the typed answer part. Once, probably today or tomorrow, after those are due, I go through and assign those points for the written part. So that usually takes me a while to get to, but you should see those points popping up after I have a chance to do that. They won't happen automatically. So that's a good question. Okay, let's look back at the, just to make sure, Olivia, did that make sense for that question you were asking about?
You just basically just run it all in that first A list, and then one variable stat, and then that's all the answers?
Pretty much, yeah.
Okay, I like that.
Yep. You do have to make sure you notice that difference between the standard deviation for a population and the standard deviation for a sample. But we're kind of used to using S right now for standard deviation for the samples. So that's the one we use. In a couple of chapters, we'll start using that sigma. So we will have to be careful about that transition. But yeah, other than that. Okay, I know we had some questions in the forums. You guys were talking about the empirical rule and the kind of interpretation of standard deviation. I do want to look at least one or two of those with you guys. Let's grab this one. So take a moment, look through that question, try to decide what you would do and what you might get, and then we'll chat about it. It is nice being able to move between all these things on Zoom, but it does move all my boxes around every time I switch. Irritating. So they have daily requests to replace light bulbs. The distribution of the number of daily requests is bell-shaped. That bell-shaped means we often refer to it as normally distributed. So that could have said bell-shaped, it could have said normally distributed. Either of those would have been the same. has a mean of 45 requests per day. That seems a lot of light bulbs. So an average of 45 with a standard deviation of 3. So standard deviation of 3, that 3 in comparison to the 45 is fairly small. So that would tend to have us think that this distribution is fairly tight. Small standard deviation relative to the mean. So it's a pretty tight distribution. Using the 68, 95, 99.7 rule, that could have just said using the empirical rule. Those are the same rule. What is the approximate percentage of light bulb replacements that are between 45 and 51? So I am going to encourage you guys to, whenever you have questions really like this, or really any question, try as much as you can to make diagrams out of it. We are visual creatures as mammals and primates. So take advantage of that large visual cortex you have at the back of your brain. That is its entire job, biggest single use area of your brain. Its entire job is to process visual information. So even folks who don't like graphs, it is a very, very powerful part of your brain. Let's use it. So our data is supposed to be in a nice bell-shaped curve. So nice bell-shaped curve. It's not too bad anyway. With a mean of 45? And a standard deviation of 3. That means we're going to go out 3 to 48. 48. And go out back 3 to 42. So that's one standard deviation above and below. An interesting kind of side note, you should be symmetrical. My drawing isn't great symmetrical wise, but you might notice on this curve here, it's essentially curving down. We call it concave down, kind of part of a bowl facing downward. Here it's concave up, it turns upward. There's a point here, it's called an inflection point, where it turns from curving upward to beginning to curve downward. That point, that inflection point, is actually where the first standard deviation is. So if you're ever looking like where on the graph should my first standard deviation be, it should be on that inflection point. Now, we are not going to worry too much about making sure our graphs are exactly precise. But for those of you who are interested in that sort of thing, it's a nice little thing to know. So between 42 and 68, between 42 and 48, 68% of our data should land in there. So in terms of our light bulbs, 68% of the days you're going to get between 42 and 48 requests. Now we were asked between 45 and 51, so we have to go out another standard deviation here. So another 3 is going to get us to 51, so that's 2 standard deviations out. If we do that in both directions, this would be down to 39. So we know 95% of our data, 95% of the number of light bulbs per day that are requested. On 95% of the days, they'll be between 39 and 51. Now, this question specifically asks us what percentage of days are between 45 and 51. So it wants this chunk. More than 45, but less than 51.
So it wants half of what, 95?
Yep. So it wants half of 95. What's half of 95? Well, half of 90 is 45. Half of 5 is 2.5. So 47.5%. So 47.5% of the days will have between 45 and 51 requests. Did the diagram help? I ask that knowing the diagram makes a big difference, or at least feeling myself, the diagram can make a huge, huge difference. Now, what if instead we had been asked, I'll give you guys a chance to play with this question. I got to get like a cut and paste normal curve, but I'll work on that. So same distribution, so 45 with a standard deviation of 3. Let's say we were asked what percent, I shouldn't do that, what percent of days have between, let's say between 42 and 51 requests.
$95.
Well, 95 is between 39 and 51. This is only from 42 to 51. So draw this diagram to kind of represent this question. So kind of draw out that diagram a bit and try to decide how you'd approach that. I'll give you a couple of minutes. Oops, that's not what I wanted. Nope, that won't work. Okay. Anybody want to venture a thought?
I think I got it.
Okay, what did you do?
47.5 plus half of 68%, which would be 34.
Perfect. So we know that this section between the 45 and the 51, we know that's half of the 95, so that's still our 47.5. But now we also want to add this chunk. And you're right, over here, the whole spot or the whole area under that curve between 42 and 48 is 68%. So that means each half of it is 34%. So that's 34% about. Again, these are approximates. We'll get more specific later on. So if we want that whole shaded area, it's going to be the 47.5 plus the 34. So what, 81.5%? Good job, Alan.
Thank you very much.
So when they talk about that empirical rule, when they say empirical rule just says that when we have a normally distributed set of data or bell-shaped data, that 68% is within one standard deviation. That's our typical data. Is the middle almost 70%, but not quite. Our between two standard deviations is the 95%. And if we went out another, say that would be what, 36 and 54, then almost all would be between 36 and 54. 99.7 is the more specific version of almost all. So 99.7 within 3 standard deviations, 95% within 2 standard deviations, 68% within 1 standard deviation. Those percentages are what the empirical rule tells us.
The empirical rule sounds like a assumption.
It is. It's based on the assumption if your data is normally distributed, we get these rules. If your data is not normally distributed, let's say, for example, if your data was really highly skewed, then that mean is being pulled off here, say. So the mean might be there where the median would be here and the mode here, for example. On a symmetric data like this, the bell-shaped normal data, the mean, median, and mode are at the same place right in the middle. So certainly if this is our mean being drugged towards the right by this skewed high data here, there's certainly not going to be the same amount on either side of that. You know, and certainly that 1 standard deviation, say we go 1 standard deviation above and below, there's a big chunk down here. So the 95%, the 68% stops being true when we have data that is skewed. But fortunately, a lot of data is normal. So we'll get to use the empirical rule a lot. And some of our tools will take our data and turn it into something that we know is normally distributed. So this restriction of it only works if you've got this kind of perfect data. It's not as big a description, as big a restriction as it seems, because one, it's called normal data because it's very common to have data look that way. And two, we'll be able to force it to happen later anyway. But you're absolutely correct. It is a big assumption, assuming your data is normally distributed. And that's why you'll see a lot of these questions right now will specify that it's either normally distributed or specify that it's a bell-shaped curve, because it has to. If not, we don't get this tool. Does that work?
Gotcha.
All right. Any of you guys have any other particular questions on standard deviation? If not,
Okay, I have a question regarding the mode, median, and mean.
Mhm.
So how do you determine the difference between the three? I know one is always center, and the mode is always at the highest point. But what about the median?
So yeah, mode is always that highest point. The median will be the central data point in order. So wherever this area is 50% and this area is 50% of your data, the mean is going to cut that 50%. 50% on this side, half the data on that side, half the data I'm on that side. The mean, where exactly the mean is depends on what the values are. So I'm putting the mean here, like putting the median here, I'm kind of making a judgment call of where it looks like this is about the same as that ish. For the mean, it really depends on what the particular values are here. So finding the mean, I'm kind of just saying around here ish somewhere. From this picture only, calculating that mean would be almost impossible. You would need the values. Does that make sense?
Yeah. So the median is always center of all the information.
Yep.
And the mean is whatever the values half of.
It's that sum of the values divided by how many values. So it's a weighted center as opposed to a position center. So it is a center that's pulled off by the high values. So if we added them all up, half of the sum would be on this side of the mean, half of the sum would be on that side of the mean, but not necessarily half of the data points.
So like the executives of a place and their salary versus the company's employees' salaries. One is going to be definitely skewed to the one side. The majority are going to be on the other side.
Right. And that's actually a nice way to look at it. With the mean, you'd have half of the payroll, how much money is being paid out to the employees, half of the payroll would be above the mean, where the median is half the employees. Oh, can't spell employees. So half of the amount of people being paid versus half of the amount actually paid. So one is just, the list of your people, the values that they get doesn't matter. But when the value they're getting paid matters, that halfway point is our mean instead of our median. If that helps. It can be subtle. What about everybody else? Tessa, Leslie, Alex, Allie, Andrea, Olivia?
I think most people are just really uncomfortable with their voice on the computer or something because
they can't sound any worse than you and I do.
No, that made total sense. Thank you so much.
I think I've got the standard deviation down. I'm more on the empirical rule. That's still tripping me up.
Yeah, that part.
I got what you just explained. I'm good on.
Any particular part of it?
I get how to set up like the diagram and to see it in the visual, but I'm not sure how to do the calculations correctly. I think I keep getting myself mixed up, and so I'm getting all my answers wrong.
One of the things that helps for some folks, and I think your textbook has a diagram like this. I'm not the biggest fan of it, and I'll tell you why as we get into it. But one of the things that you'll often see is people take the diagram that we've been using, so that's your mean, and then 1 standard deviation off, 2 standard deviations off, 1 standard deviation below, so I'm going to call it negative, 2 standard deviations below, negative, and then 3, and stuck in there, 3. And instead of looking at the 68 and the 95 and so forth, what they'll do is they'll break up each of these sections, so essentially 1, 2, 3, 4, 5, 6 sections, and break each of those sections into pieces. So like up here, that 34%, each of these sections are 34% of your data. these sections here, well, we found that this whole half was 47.5, and this first part should be another 34. So if we subtracted those, this piece here is 13.5%. Does that make sense?
True on both sides.
Same on both sides. Yeah, 13.5% down there too. So some people like to look at it kind of section by section instead of this chunk and that chunk. What does that mean is left here and here? Kind of depends a little bit on how you look at it. If this is 95%, this is what I prefer to do. If this is 95%, then there's got to be 5% on the outside, which means there's 2.5% on either side left. Now, the issue is that that is all the way out as opposed to just to that third standard deviation. So that doesn't take into account that 0.7 as opposed to 100%. So you could modify this to what you'd have to take out 0.12. So that would be 2.47? No, 2.37. So 2.37 if you wanted to go just that chunk out to 3 standard deviations, and then 2.37 if you wanted to do the chunk just out to 3. So go ahead.
Is my math, my open math, what are they going to want as far as that answer whenever they ask?
It depends on what they ask. If they ask specifically, like say they were asking out to 45, out to 54, then you'd need the 2.37. If they said, like say 45 and up, so it could go up indefinitely, you'd need the 2.5. So it depends on whether you're using that 3 standard deviation value as a barrier or if you're just saying, and anything bigger. Fair?
All right. Well, as long as, you know it and they know it, and yeah.
So some people like this better because you don't have to do kind of some of the little cutting up that we did up here every time. Of the 60, what part of my 68 am I using? It's less kind of a creative way to cut it up and just add up the sections. So if you just want these two, then you add those two together and you get to 47.5. If you want this section, that section, and this section, add them all up. They'll add up to the 81.5. The reason I don't like this as much is you're essentially then encouraged to memorize these. So you'd be memorizing the 68%, you'd be memorizing the 95%, you'd be memorizing the 99.7%, and you'd be memorizing where the 34% are, and the 13.5%, and the 2.37%, and while we're at it, the 2.5%. Memorizing those extra ones is hard. It's a lot more to memorize. If you have these 3 down, then you can build this whenever you need to. Fair? But when you're first learning how to answer all these questions, looking at it this way for a while can be real helpful for some people because you're not having to both think about what the question's asking and think about all those calculations both at the same time. So, Allie, I don't know if that helps, but...
Yeah, that did. That made a lot of sense when you explained it, because I've seen that in the book, but when you're just reading it, it doesn't make sense.
Well, and it looks like it's a different, I thought the empirical rule was the 68 and the 95, and then it's kind of saying this empirical rule is the 34 and the 13.5. Which one is it? This is a consequence of the empirical rule. So, if that helps, great. You guys got anything else out there? So then my question is, do you guys feel sufficiently comfortable with that you want to start talking about our other version of spread? Because again, this is the version of spread that goes with mean. So this is mean was our center by value. Standard deviation is our spread by value. That median was the center by position. We have a sense of spread that goes along with median. That's a spread by position. So are you guys comfortable with this, that you want, that you're comfortable going on to talking about our other types of spread? Or would it be better, we don't have that much long left today, would it be better to just kind of leave this, let you guys practice that standard deviation stuff more before we add that other spread on top? What are your feelings and or opinions?
I'd like to wait until tomorrow just so that I can finish the homework that was due yesterday.
Well, what
And
I can do then is I can go in right here and move that, the 3.2, because I noticed a lot of the scores on the 3.2 aren't great. But I can
Yeah, I need
take
some more
that.
practice too.
Yeah, I used to late pass.
So I can go in and just move that homework so you guys don't have to use a late pass. If you already did, I can give that late pass back to you, so don't worry. But I
Thank
can
you.
move that 3.2
Jinx, Olivia, you owe me a Coke.
to, how about Wednesday, just so in case you guys have other questions tomorrow. So you guys can play with that. Because really getting comfortable with standard deviation and that empirical rule is super, super, super important. Not just the empirical rule specifically, but just understanding and getting comfortable with the concept of standard deviation is super important because we're going to use it so much. And later on, chapter 7 is really diving into this distribution, this curve, and being able to say, okay, within 1 or 2 standard deviations, we know their percentages, but what if it's 1.5 standard deviations or 1.3 standard deviations? What percentage is that in there? So we're going to get to a point that we can cut this thing up into any little subdivisions we want. And being super comfortable with this is really going to help when we add that complication onto it later. Fair?
Yes.
Yeah, that doesn't sound complicated at all.
Well, and by the time we get there, it's actually not that bad, but it is something that something that we have to get practice with. There are 2 more little details with standard deviation that I want to talk about then, just before you guys head out. Which one do I want to do first? Let's do that. So let's say we have a data set that has an X bar, has a mean of 14, and a standard deviation, S, of, say, 3. So big data set, however big the data set might be. Given a specific data point, an individual data point, so an X value of all of those possible X's, given the X value of 18, so that 18 is higher than our average, so it's a large data point, and it's actually even more than 1 standard deviation away from the mean, so it's not typical, but we still wouldn't call it unusual because it's not outside 2 of those. Remember, typical is 1 standard deviation, usual is 2. So this wouldn't be considered unusual. We'd have to get to 20 before they're unusual, but it is higher than typical. One of the things we will be asked here is, what is this value's Z-score? Questions about the test will answers be multiple choice? No, most of the questions on the test are not multiple choice. They look a lot like your questions of from the homework. So there's some multiple choice, but usually not very many, if any. So I want to talk real quick about what a z-score is, because we'll use that terminology more and more as we go along. And particularly when we get to that chapter 7, we'll use it a lot. So a z-score is, roughly translates, actually almost directly translates into how many standard deviations above or below. Sometimes you'll just hear people say how many standard deviations from, but above or below the mean is the value, is the data point. So this 18, the z-score just tells us, its only job is to tell us how many standard deviations above or below the 14 is this 18. Now, just looking at it, we could see that it's more than 1, right? So our z-score will be more than 1 because 18 is more than 1, 3 from 14. But how we can calculate that fairly easily, and getting used to this formula is going to be handy, is find out, well, how much is it deviating? How far from the mean is our data point? So take our data point, subtract off our mean, and divide that by our standard deviation. So we'll find out how far away it is and how many standard deviations is that. So 18 minus 14 divided by 3 is going to give us 4/3. So our z-score would be, we could just say it's 4/3, but if you want to approximate it, and we usually will, that's 1 1/3, so 1.33. That's our z-score. So 18 is 1 1/3 or 1.33 standard deviations above the mean. So for right now, we'll just be calculating that z-score. But as I said, later on, we'll use it for quite a few things. So it is something that getting used to calculating is going to be handy. Say, for example, we wanted the z-score for, how about 12? So I want the z-score for 12. Same process. 12 minus 14 divided by 3. Value minus mean. Make sure you get this order correct. Here it's going to be negative, and I want it to be negative because that negative is going to tell us it's below the mean. So a z-score of negative 0.67, a little less than 1 standard deviation from the mean. So the big thing to kind of get from this is what is a z-score? It is this formula. It's how we calculate them. But what does it represent? It represents how many standard deviations we are from the mean. So you'll start seeing that pop up pretty soon. Let's see, what else? Ooh, yeah, last thing before I let you out. There's a question on the homework that often drives a lot of people nuts. It says, it's something about years that teachers have been working. So years working at a particular school. And they know the standard deviation is 6.
Mhm.
But they can't remember 6 what? Anybody play with that question?
Yeah, it was like 6 months, 6 years, or 16 years.
So 6
Yeah.
months, 6 years. I think it was 6 decades, wasn't it?
That would be
16 years.
Yeah, I think it was 16 years.
Yeah, I'm on the question right now.
Oh,
16.
16 years? Oh, was
Yeah.
16? Okay. So 16 months, 16 years, or what's the other one?
No, it was 6 months, 6 years, or 16 years.
Oh, okay. Gotcha. So 6 months, 6 years, or 16 years? Okay. And a lot of people looking at this question say, well, I don't have enough information to calculate this. And you're not supposed to have enough information to calculate this. The idea here is all about what does standard deviation mean? What does it represent? So let's say the average teacher had been working at the school for, I'm just going to make this up, 8 years. Fair?
Yes.
If the years, yeah. If the standard deviation was 6 months, that means that almost all of the instructors will have worked 8 years plus or minus 3 standard deviations. Remember, almost all is 3 standard deviations, usual is 2, typical is 1. So 3 of these would be a year and a half. So up to 9.5 years and down to 6.5 years. So if this 6 months is your standard deviation, then almost 100% of your instructors will have worked between 6 years and 6.5 years and 9.5 years. That is a very tight spread for all of your teachers. Fair?
Mm-hmm.
If the 6 years is our standard deviation, then 3 of those would be 18 years. So that would be what, 18 plus that's 26. 18 minus that is, well, 0 or less. Fair?
Yes.
So that means all of your instructors will have been either brand new or been working all the way up to as much as 26 years. So instead of the newest teacher being 6.5 years, the newest teacher is a new hire. The teacher who's been there the longest has been there 9.5 years, or the teacher that's been there the longest has been there 26 years. Which of those two seems more reasonable for this data set?
Well, 6 years, but you didn't actually even say anything about the 16.
Well, let's talk about the 16. So 8 years. What's 3 times 16?
32
48.
plus 16.
So 48. So 48 years would be what, 56 years, or down to, the negative 40 years, which of course it can't go below 0. But that would mean there's a lot of new hires. And the longest person there has been working there for 56 years. That's possible.
Sounds legit.
It could happen. Which do you think is more probable?
That the 56 years is the cafeteria lady.
Said faculty.
The librarian.
Not faculty.
Really? Okay.
That's classified staff.
All right. Get rid of the 16 years.
All right. And particularly it going this far down means you've got so many people down in this who are new hires. And it certainly could happen. Any of them could happen. Any of them are possible. But which one do we think this was probably? Based on the size of the data set and what's being talked about, that 6 years is much more likely. So this question is really about, are we conceptualizing what standard deviation means? Most teachers, or 68% of the teachers, should be within 6 years of the average. It'd be unusual for somebody to be more than 12 years from the average. Everybody is within 3 standard deviations, so everybody is within 18 years. That's fairly sensible. So that's what this question is really kind of getting at, is does the concept of standard deviation make sense in terms of scale?
Wasn't this also, Olivia, you're on that page, is that correct?
Yes, I am.
So wasn't part of this question where you had to fill it in with a verbal answer?
Yes, there is.
And what was the question?
It was just where it just asked you why. Like, why do you think it was that answer if you got that first portion right of selecting 6 months, 6 years, or 16 years?
So
If that makes
answering
sense.
that question, teacher,
Mm-hmm.
how would you ask us to verbalize?
Well, I would like for this, I would say I would put 6 years, right? And say, I think it's most reasonable that instructors would be within 3 of those 6 years, so within 18 years of an average, as opposed to within 18 months of an average. And having, the typical instructor being 16 years out seems like far too wide of a range. So just the kind of things I've been saying.
Okay.
Or even things like it said, consider the empirical rule specifically. The idea that 99.7% of all instructors are within 18 months of each other seems unrealistic.
Not in Chicago at a high school.
And that's why, again, all of these things are possible. But which one is probably the most likely? That's 6 years. And the nice thing about having that verbal answer, one of the reasons that verbal answer is there, is if you said 6 months and your verbal answer very appropriately discussed why you thought it was, and you used things like the empirical rule and the meaning of standard deviation, correctly, you just thought 6 months was more appropriate because, you are thinking about, turnover and all that kind of thing. You can still get most, if not all, the points on that question if it's expressed properly. So,
Okay.
In my experience of teaching in the inner cities of Chicago, no teacher lasts more than 1.5 years or 2 years before they quit. So having, 70% of the teachers not teach for more than half a year.
That sounds about right.
Yeah, that's my experience with, and that would be a great answer. I'd be like, awesome. But it would have to be a pretty extreme situation. Okay, well, we ended up filling all our time, which is great. Play with this stuff. I did move that assignment to being due. Send me a message if you used a late pass so I can give you that late pass back. And have a wonderful day. If you need anything else, let me know.
Consider this your message. I used a late pass.
I will forget that. So if you're okay with me forgetting that, then that's fine.
Okay.
Thank you.
Thank you so much.
You're very welcome. Have a wonderful day.
You too. Bye.
Bye-bye.
Bye, everybody.